In this video, we're going to have a look at proving some of the circle theorems. In particular, we're going to just focus on angles within the circles. So just to review the features of a circle, we have obviously the whole circumference, which is the whole perimeter of a circle. And when we take a part of that circumference, we call that an arc. We've got that in green, which is an part of the circumference between 2 points. In fact, the green represents a minor arc of this circle, and so the other arc that's left over is the major arc. You can see here it's much larger. We have a chord, which is a straight line going from one point to another on the circumference of a circle that is not through the centre of the circle, and that's called a chord. And then what a chord does is breaks our circle into two parts. We've got two segments. Here we've created a minor segment, and the larger part is called our major segment. And in red we have one of the final main features in a circle is where we draw a tangent to the circle. A tangent is a straight line that touches the circle at only one point. So let's begin having a look at the link with the angles at the centre of a circle compared to the circumference. Prove the angles at the centre of the circle are twice the angle at a circumference when they're subtended by the same arc. So here we have the points A and C, and we have that major arc A and C. And we can see that point B lies on that major arc, and we've created some chords here and some radii through the centre of the circle, which is O. So in order to prove this, I'm going to actually split this up into two isosceles triangles using the radii of the circle. And I'm going to focus on how can we define this angle here being twice the angle at the circumference. So first of all, I'm going to define this angle here as angle A and the angle on the other side around the origin of the circle or centre of the circle as B. So looking at the fact that I've got two isosceles triangles, in my first triangle here in green, I'm going to call the angles in here X because it's an isosceles triangle. So I can see that angle A is 180 take 2 lots of X. And in my other triangle, my isosceles triangle OBC, I'm going to call the angles both Y because they're both equal. So angle B would be calculated by 180 take 2Y. So let's call this angle at the centre C. So therefore angle C, which is just going to be 360 degrees take angle A and take angle B. Neatening this up, we end up with 360 take 360 and 2x plus 2y because of those negatives. So that means if we take a common factor of 2, x is 2 lots of x plus y. And we can see that the angle ABC is represented by x plus y. Therefore, the angle at the centre, AOC, which we've called angle C, is represented by 2 lots of xy, which is 2 lots of, that angle at the circumference. So we have proven the first circle theorem. The angle at the centre is twice the angle at circumference when subtended in the same arc. Just to note that this theorem doesn't always look really nice as in our example, first one that we've proven. We might actually get points on an arc like so. We could call this point A, we could call this point C, and we can see the angle at the centre is actually a reflex angle. It is still twice the angle at the circumference when it's subtended by that same arc through AC. So let's take a look at the question. So I can see a circle where I've got some points on the circumference. I could call these two bottom points A and C, creating the arc AC and the point B. And I've created some angles from these points in that arc. So what I want to do is find the value of X, Y, and Z. Most important, showing reasoning. So I'm going to start with finding X because I can see that it's an angle on the circumference, and I have the angle at the center in that arc. So I'm going to say X is going to be a half of 118. So X is going to be 59 degrees. And my reason for that is the central angle theorem. This tells me the angle at the center is twice the angle at the circumference. So X will be half. From here, I can find Y. Y is around that central point, so it's going to be 360. Subtract 118, so Y is 242. And the reason is angles at a point sum to 360 degrees. And therefore, I can now find Z. So Z, if I have a look, because I know what Y is an angle at the center through the minor arc AC, and Z is the angle at the circumference. So Y is going to be twice what Z is, or Z is going to be half Y. So Z is going to be half of Y. So Z is going to be 121 degrees, and the reason is the central angle theorem. Now I'd like you to pause the video and have a go at question 2, and then come back and have a look at a sample solution. So we have our circle with all the information of the points A, B, C, D lying on the circle. Let's have a look at another theorem. Angles on the circumference of a circle subtended by the same arc in the same segment are all equal. So we're actually going to complete the proof of this in an exercise question 6. So I'm not going to show you the proof of this right now, but basically it's saying that if we've got this arc through A and say D, in this minor arc, we've created these angles where the X is formed, and we could call that through point B and perhaps through a point C. If we're using that same arc, subtending right through to the circumference, then these angles will always be the same. So I could put in a point E here, and that angle will have the value of X, just like the other angles. So let's see this in action. This one says, find the value of the unknowns in the following giving reasoning. So here, I'm just going to label some points to help me. I'm going to call this A, B, C, D, and I can see I've got the central point, so I'm going to give that an O. And here I want to find M and N. What I can see is I've got a minor arc through A and D, and I've created the angles M and the angles N using this minor arc. But I also have created a central angle that's 40 degrees. I know that that angle AOD at the center is 40 degrees. And I know that angle ABD is going to be exactly half of 40. That's because I've got the central angle theorem. So this is telling me that angle ABD, which is represented by M, is 20 degrees. So therefore, because I know that angle ABD is equal to angle ACD, because angles through the same arc on the circumference are equivalent, that tells me that M is N, so N is also worth 20 degrees. The reason for that is angles at the circumference through the arc, and I've called my arc AD, are equal. So now I'd like you to pause the video and have a go at part B. And I'm going to put a solution here for you. So have a pause and have a go, and then come back and check a solution. You can see I've actually given two sort of possible ways of working through a solution to this. Okay. And our last circle theorem that we're going to have a look at is the angle in a semicircle. It says prove an angle at the circumference subtended by a diameter is actually forming a right angle. You can see by the picture, I've got my diameter going through from point A to point C through the centre O. And so I've got the arc AC, and I've got a point on the circumference B that is in that arc. And when I create that, what essentially looks like a triangle, I'm going to have a 90 degrees at point B. So we want to prove this. So we want to prove that angle ABC is actually 90 degrees. Well, I can clearly see that I've got a triangle here. So what I'm actually going to do is draw a radius from O to B. And what essentially I then have is 3 radii drawn, one from OB, one OA, and one for OC. I'm going to have a look at triangle OAB, and I know that this triangle is an isosceles triangle. And that's because OA and OB are equivalent because they are the radii of the circle. So I'm going to let angle OAB and OBA, because they're going to be equal, to represent x. I'm going to call this angle x and angle x. Now, if we look at the other triangle that we've created, OCB, so in triangle OCB, I know that this is also an isosceles triangle because OC and OB are equal because they're also both the radii of the circle. So we're going to let angle OCB and OBC equal y. So for the large triangle, so for triangle, I can add up the angles to sum this triangle to 180 because I know that's going to be the sum of the angles. We've got an x plus a y plus an x plus y, and that's got to equal 180 degrees because that's the sum of the angles in a triangle. So if I collect my like terms, I've got 2x plus 2y equals 180 degrees. Taking out a common factor, so it tells me that x plus y is 90, therefore angle ABC is 90 degrees, and we have proven that theorem. So if we're ever using the diameter of a circle and we're using through that arc a point on the circumference, it will always be 90 degrees. So taking a look at a question, we've got a circle. We can clearly see we've taken a diameter from P to Q through the central point O. So we know that angle PRQ is equal to 90 degrees because of the angle in a semicircle that we've just proven. So that is 90 degrees at point R. So if we sum the angles, we've got x plus 90 plus 48 degrees. They should equal 180 degrees for the sum of the angles in a triangle. So x therefore must equal 42 degrees. Now I'd like you to have a go at part B and pause the video and then come back and look at the sample solution, making sure that you give reasons. You might like to redraw parts of that diagram from PSRQ so that you can see how Z and X and Y relate to the angles 23 and 20. Don't forget to look for some angles in a semicircle.